It is now. All right. So now this is the language of physics, and we're slowly developing this. So we're looking at forces. We started with scalars and vectors last week, and today we're going to look at contact and non-contact forces. Some of you may have already done this or come across this before. I do mention them within physics, but we're going to really take our time, and I'm going to be very, very clear about this. Every word I'm going is in English, but this is not English. This is physics. So the words have definite and precise meanings in physics, and we've got to get kind of used to that in a way that when I talk about weight, and I was talking to year 11 about going to the gym yesterday, and we're talking about weight, and we talk about kilograms in normal language, but in physics we talk about weight being in newtons, and it's a force. Anywho, we're going to talk about forces, non-contact and contact forces. So a contact force is where something is touching something else. It must physically touch. Pushing a bike, doing things of that nature, pulling a sledge, when it's snowing, you pull a sledge. These are contact forces you must be touching. One of the really common ones is friction. Friction is when two things rub together, right? And it's almost as if I've got this picture of this car. The engine is producing a thrust, right? This direction. But we're looking at air resistance. This is drag. It's almost, so force is a pull or push. It's almost as if friction is a very cheeky little monkey sat here going, ha ha ha, it's a little gremlin, holding onto a rope and pulling you backwards. So drag, air resistance, friction is a pull. Okay? All right. Now, the second description I've got here is tension. And I really like tension. The reason I like tension is it's not the word tension when you're really stressed out. And I remember being very young, and when I went to primary school, you could do things like play tug of war on sports day. And I want you to think, this person here is pulling to the right, this person here is pulling to the left, and there are two forces in play, and there is tension in the rope. Okay? So when we look at its description, it's the force, newtons, transmitted through a cable, a rope, or a string when it's pulled. And they are in opposite, the forces are in opposite directions. Well, they must be. Because if this guy's pulling to the right, and this person's pulling to the right, everybody's moving to the right, and there's no tension in the rope. Okay? So there must be an opposite ends. Now, the other thing that I'm going to introduce you to, you're only year 7, all right? So it's the reaction force, or the normal contact force. So what Newton said, Sir Isaac Newton, and we use his full name, Sir Isaac Newton, and we just had his birthday. So Isaac Newton's birthday was on the 25th of December on Christmas Day. And what he said is, to every force, there is an equal and opposite reaction. There's an equal and opposite force. Right? So when you put a weight on a table, the weight is pushing downwards. However, the table is pushing upwards. And that's really weird. You just think, well, how comes the table can't be pushing upwards? It does. Okay? But we're not really going to go into it does, and when we are going to look at it in more detail in the next couple of weeks. But right now, just remember, if there's a weight downwards and it's sat on something, it's not moving, there is a normal reaction force upwards, a normal contact force upwards. It is always 90 degrees to whatever it's sat on. So it's sat on this table, and we use the word perpendicular. There's another word. It's 90 degrees to whatever it's sat on. So if it was a slope, and I had this block sat on a slope, then the normal contact force would be 90 degrees to the slope. All right. And as I said, you're just getting used to this. Okie dokie. Now, upthrust, right, is the upward buoyancy. That means when something's floating, it's being pushed upwards, right? And it's an upward buoyancy force exerted by a fluid. We generally talk about water on an object. And I put a picture of upthrust. Now, as you go down, the pressure increases. So the water actually is pushing against, well, this is a little, let's say, a ball in the water. It pushes it and it squeezes it upwards. And that is upthrust. There's a force squishing it. Compression, this is in springs. And it's a squeezing force. Right? You squeeze, not squeeze, it squeezes it. Right? Your force is pushing inwards and squishing it. It's a squishing force. Okay, non-contact forces. They don't have to touch. And she was like, what? All right, you jump out of an aeroplane, you don't have to touch the ground for it to pull you down. And even in space, where no one can hear you scream, when you jump out of an aeroplane. Okay, gravity will pull you down, but it doesn't need to touch. All right. So now, no, if I give you a test, and I like giving you odd questions, so it's not really a test. But if you ever do a test and it says, what is, and give me a non-contact force, to be precise, it will be gravitational attraction, not just gravity. Or it'd be weight, but I prefer the term gravitational attraction. Now, here's another cool word, electrostatic force. Things can be charged positive and negative. If they're the same charge, positive, positive, or negative, negative, they push each other apart, they repel, they're repulsive. If they're opposite charges, they attract. You get that with magnets. If you play with magnets, if you get north and south poles, they stick together, you can pull them apart. But if you get two north poles or two south poles, they repel. All right. As always, I've given you a set of questions. These questions are all about, you are going to have to go back and read some of these really short keywords that I've put here and key ideas. But it's all about two things. You getting used to the language that we're using. All right, darlings. 7 minutes. Ooh, I love intros that are 7 minutes long.